In the depths of space, something waits that makes every nightmare seem gentle. A supermassive black hole, 40 billion times heavier than our sun, devours the equivalent of an entire star every single day, while another monster fires runaway stars at us like cosmic bullets traveling millions of miles per hour. These are not distant fantasies, but real terrors lurking in our universe right now. Tonight, we journey to the most horrifying black holes ever discovered, from the stellar corpses that could spaghettify your body in seconds, to the galactic titans that could swallow our entire solar system and still hunger for more. You will witness time itself bend and break, matter heated to temperatures that dwarf the sun, and gravitational forces so extreme they tear reality apart. Like and subscribe if you dare to explore the cosmos with us. Prepare yourselves. We begin. Imagine a place where the laws of physics you trust completely break down. Black holes represent the ultimate cosmic nightmare because they violate every instinct we have about survival. You cannot outrun them. You cannot hide from them. Once you cross a certain invisible line called the event horizon, not even light itself can escape. Think of it like falling over the edge of a waterfall that stretches infinitely downward, except instead of water, you are falling through the fabric of space and time itself. What makes these objects so fundamentally terrifying is their relationship with matter. A black hole forms when a massive star collapses under its own gravity, crushing all that mass into a space smaller than a city. The result is a gravitational field so intense that it warps reality around it. Picture space like a stretched rubber sheet, and a black hole as a bowling ball placed on that sheet, creating a deep well that everything nearby rolls toward. But here is the truly horrifying part. Black holes are not rare cosmic curiosities. Scientists estimate that our galaxy alone contains 100 million black holes, most of them stellar mass monsters between 5 and 50 times heavier than our sun. They lurk in the darkness between stars, invisible except for their gravitational effects on nearby matter. The terror multiplies when you realize how black holes feed. As matter spirals toward the event horizon, it heats up from friction, glowing brighter than entire cities. This feeding process creates an accretion disk, a swirling vortex of superheated gas that can stretch for millions of miles. The temperatures here exceed 10 million degrees Fahrenheit, hot enough to strip electrons from atoms and create a plasma hell that would vaporize any known material instantly. Even more disturbing is how black holes manipulate time itself. As you approach the event horizon, time slows down dramatically compared to the outside universe. To someone watching from a safe distance, you would appear to freeze at the edge, your image fading as the light from your body gets stretched to longer and longer wavelengths until it disappears entirely. Meanwhile, you would experience time normally as you fall toward the singularity at the center. The singularity itself represents the complete breakdown of our understanding of physics. Here, all the mass of the black hole concentrates into a point of infinite density, where the curvature of space-time becomes infinite. Scientists cannot describe what happens at this point, because our equations simply stop working. What makes this even more unsettling is that black holes are not just destructive forces. They play crucial roles in galaxy formation and evolution, sitting at the centers of nearly every large galaxy like cosmic engines. The monster at the center of our own Milky Way weighs 4 million times more than our Sun. The stellar graveyard around us holds horrors beyond imagination. Every black hole begins as a star, but not just any star. Only the most massive giants, those at least 8 times heavier than our Sun, can create these cosmic monsters. When such a star exhausts its nuclear fuel, it faces a catastrophic end. The core collapses in less than a second, rebounding in a supernova explosion so violent it can outshine an entire galaxy for months. What remains after this stellar death is a corpse more dangerous than the living star ever was. The core, now compressed to densities that defy comprehension, becomes a black hole. Picture taking all the massive Mount Everest and crushing it into a space smaller than a grain of sand. That gives you some idea of the incredible density we are dealing with. These stellar mass black holes typically range from 5 to 50 times the mass of our Sun, but they occupy a region smaller than most cities. The event horizon of a 10 solar mass black hole measures only about 60 miles across. Yet this tiny region of space creates a gravitational field so intense that it can tear apart anything that approaches too closely. The most terrifying aspect of stellar mass black holes is their abundance and proximity. Scientists have identified around 50 confirmed or suspected stellar mass black holes in our galaxy alone, but theoretical models suggest there could be 100 million of them scattered throughout the Milky Way. They drift through space like invisible predators, detectable only when they interact with nearby matter. The closest known black hole to Earth sits just 1/500 light years away in the constellation Telescopium. This monster, called HR 6819, weighs about 8 times more than our Sun. While that might seem comfortably distant, in cosmic terms, it practically sits in our neighborhood. Most stellar mass black holes remain hidden in the darkness, but some reveal themselves through their feeding habits. When a black hole has a companion star, it can slowly steal matter from its neighbor. The stolen gas spirals into the black hole, forming an accretion disk that glows with X-ray radiation. These X-ray binaries appear as flickering points of light that betray the presence of the invisible monster. The feeding process creates a cosmic dance of destruction. The companion star, typically a normal star like our Sun, gradually loses mass as the black hole strips away its outer layers. Over millions of years, the black hole can completely devour its partner, leaving behind only the gravitational disturbance of its own presence. Perhaps most disturbing is how stellar mass black holes can remain active for trillions of years. Unlike stars, which burn out and die, black holes grow stronger with time. Every particle they consume adds to their mass and extends their event horizon, making them more dangerous to anything that ventures too close. Your body becomes a noodle, stretched beyond recognition in the most horrifying way imaginable. Spaghettification represents one of the most visceral terrors that black holes inflict on matter. The process begins innocently enough as you approach the event horizon, but quickly transforms into a nightmare of physics that tears apart everything it touches. The name itself comes from the way objects get stretched into thin, elongated shapes that resemble strands of spaghetti. The horror starts with a simple fact about gravity. It weakens with distance. This means that if you fall toward a black hole feet first, the gravity pulling on your feet will be significantly stronger than the gravity pulling on your head. For a stellar mass black hole, this difference becomes extreme very quickly. Picture yourself 6 feet tall, falling toward a black hole with 10 times the mass of our sun. When you reach about 400 miles from the event horizon, the gravitational difference between your head and feet becomes equivalent to hanging an 800-pound weight from your ankles. Your body begins to stretch as the tidal forces overwhelm your structural integrity. The stretching intensifies as you fall closer. At 200 miles from the event horizon, the differential force increases to several thousand pounds. Your bones begin to crack under the strain. Your muscles tear. Your organs distort beyond recognition. The process is not quick or merciful, but gradual and inexorable. But spaghettification does not stop at stretching. As your body elongates vertically, it also compresses horizontally. The same tidal forces that stretch you from head to toe also squeeze you from side to side. Imagine being pressed through a cosmic pasta machine that stretches you longer while making you thinner. The mathematics of this process are as terrifying as the experience itself. For a human body near a 10 solar mass black hole, the stretching force increases by roughly 6 million times what you would experience on Earth. No biological material can withstand such forces. Your body would literally be pulled apart at the molecular level. Different types of black holes create different spaghettification experiences. Smaller black holes are actually more dangerous because their tidal forces are stronger near the event horizon. A 3 solar mass black hole would spaghettify you well before you reach the event horizon, while a supermassive black hole might allow you to cross the event horizon intact. The process affects more than just living things. Spaceships, asteroids, even entire planets would undergo spaghettification if they ventured too close to a black hole. The only difference is the distance at which the stretching begins. Larger objects start feeling the effects farther away because the gravitational difference across their greater size becomes noticeable sooner. Scientists have actually observed spaghettification in action when black holes tear apart stars. These tidal disruption events create spectacular displays of cosmic violence as stellar material gets stretched into long streams of hot gas. Cross this invisible line, and you have just signed your death warrant in the most absolute way possible. The event horizon represents the ultimate point of no return in the universe. This invisible boundary surrounds every black hole like a spherical cage made of warped space-time itself. From the outside, it appears as nothing more than empty space, but crossing it seals your fate more completely than any prison ever could. The name itself reveals the horror. It marks the horizon beyond which no events can ever be observed by the outside universe. Once you cross this boundary, you become permanently cut off from the rest of reality. No signal, no light, No information of any kind can escape to tell the universe what happened to you. For a stellar mass black hole weighing 10 times more than our sun, the event horizon sits about 60 miles from the center. That might seem like a reasonable distance. The gravitational field here is so intense that escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing can escape. What makes this trap so insidious is how normal everything feels as you approach it. You can see the event horizon coming, but you cannot feel anything special about crossing it. There is no wall, no barrier, no sensation of passing through anything significant. You simply fall through empty space that happens to be curved in the most extreme way possible. The true horror becomes apparent when you try to communicate with the outside world. As you approach the event horizon, any light you emit becomes increasingly redshifted, meaning its wavelength stretches to longer and longer values. To observers watching from a safe distance, you appear to slow down and fade away, your image frozen at the edge of the event horizon as the light from your body gets stretched into invisibility. Meanwhile, you experience time normally. You watch the universe outside the black hole speed up dramatically as you fall. Stars leave and die in what seems like moments. Galaxies evolve and change. The cosmic microwave background radiation gets blue shifted to higher and higher energies, eventually becoming a deadly torrent of gamma rays that would fry any living thing. The event horizon also marks the boundary where space, time curvature becomes so extreme that straight lines no longer exist in any meaningful sense. Every possible path through space leads toward the singularity at the center. Even light, which normally travels in straight lines, follows curved paths that spiral inexorably inward. Perhaps most disturbing is the realization that the event horizon is not fixed in size. Every particle that falls into the black hole increases its mass slightly, which expands the event horizon outward. The black hole literally grows larger with each meal, becoming more dangerous to anything that ventures nearby. The event horizon represents more than just a physical boundary. It marks the edge of noble reality, the point where the familiar laws of physics begin to break down completely. In the heart of every galaxy lurks to be so massive it defies comprehension. Supermassive black holes represent a completely different category of cosmic horror. These monsters weigh not just dozens of times more than our sun, but millions or billions of times more. They sit at the centers of galaxies like gravitational anchors, their influence reaching across hundreds of thousands of light years to shape the very structure of their cosmic neighborhoods. The smallest supermassive black holes contain the mass of 100,000 suns crushed into a region smaller than our solar system. The largest discovered so far weighs over 100 billion solar masses, containing more matter than the entire Milky Way galaxy. These titans make stellar mass black holes look like cosmic dust particles. By comparison, what makes supermassive black holes truly terrifying is not just their size, but their hunger. When they feed, they create some of the most violent phenomena in the universe. Matter falling into these monsters accelerates to incredible speeds, heating up to temperatures of millions of degrees. The resulting accretion disk can outshine billions of stars, creating quasars that we can observe from across the entire universe. The feeding process creates a hellish environment around the black hole. Gas and dust spiral inward at nearly the speed of light rubbing against itself with such violence that it emits intense radiation across the entire electromagnetic spectrum. X-rays, gamma rays, and radio waves pour out from the accretion disk with energies that would sterilize any planet within thousands of light years. The gravitational influence of these monsters extends far beyond their event horizons. A supermassive black hole can gravitationally bind entire star clusters, forcing thousands of stars to orbit around it in tight formations. Some of these orbital velocities reach thousands of miles per second, creating cosmic hurricanes of stellar material. Perhaps most disturbing is how supermassive black holes seem to control the growth and evolution of their host galaxies. Observations reveal a tight correlation between the mass of a galaxy's central black hole and the mass of its central bulge of stars. Somehow, these monsters regulate star formation across their entire galaxies, acting like cosmic thermostats that control the temperature and density of galactic gas. The event horizons of supermassive black holes can span distances larger than our entire solar system. The black hole at the center of the galaxy Messier 87 has an event horizon with a diameter of about 24 billion miles. You could fit the orbits of all the planets in our solar system inside this region with room to spare. The most unsettling aspect of supermassive black holes is their apparent immortality. While stellar mass black holes eventually evaporate through a process called Hawking radiation, supermassive black holes are so large that they would take longer than the age of the universe to evaporate completely. They represent eternal cosmic predators that will outlive stars, planets, and possibly the universe itself. 26,000 light years away, a monster watches us from the heart of our galaxy. Sagittarius A star sits at the center of the Milky Way like a cosmic spider in its web, weighing over 4 million times more than our Sun. This supermassive black hole represents our nearest galactic neighbor of ultimate destruction, and its influence reaches across the entire galaxy to affect every star, planet, and potentially every living thing within hundreds of thousands of light years. The beast hides behind thick clouds of gas and dust that obscure it from direct observation in visible light. But astronomers have tracked stars orbiting around this invisible monster, watching them accelerate to incredible speeds as they swing past the black holes of an horizon. Some of these stars reach velocities of over 5,000 miles per second, moving so fast they would cross the entire United States in less than a second. One star, designated S2, follows such an extreme orbit that it passes within just 8 billion miles of the black hole's event horizon. During its closest approach, this star experiences time dilation effects and gravitational redshift strong enough to test Einstein's theory of general relativity. The star's light gets stretched to longer wavelengths as it climbs out of the black hole's gravitational well, providing direct evidence of the monster's terrifying power. The event horizon of Sagittarius A star spans about 24 million miles across, roughly the size of Mercury's orbit around the Sun. Inside this invisible boundary, the laws of physics, as we know them, cease to function normally. Matter, energy, and information disappear forever into a realm where space and time become meaningless. What makes this monster particularly unsettling is its current state of relative quiet. Unlike many galactic centers, Sagittarius A star is not actively feeding on large amounts of matter. It sits dormant, occasionally flaring with bursts of radiation when small amounts of gas fall into its accretion disk. But this dormancy may not last forever. Scientists have observed periodic flares from the black hole's region, suggesting that it sometimes swallows asteroids, comets, or small clouds of gas. Each feeding event produces a brief but intense burst of radiation that can be detected across multiple wavelengths. These flares remind us that the monster is still very much alive and dangerous. The black hole's gravitational influence extends far beyond its immediate neighborhood. It helps stabilize the orbital motions of stars throughout the galaxy, but it also poses a long-term threat to our solar system. As the Milky Way evolves over billions of years, changes in the galactic structure could potentially alter our orbit around the galactic center, bringing us closer to the central black hole. Perhaps most disturbing is the realization that Sagittarius A star could potentially become active again. If a large gas cloud or even another star fell into its accretion disk, the resulting energy release could sterilize large portions of the galaxy with intense radiation. Black holes have been firing stars at us like cosmic cannonballs, traveling millions of miles per hour. The discovery of hypervelocity stars represents one of the most terrifying revelations about black hole behavior. These stellar projectiles race through space at speeds exceeding 1,000 miles per second, fast enough to escape the gravitational pull of entire galaxies. They represent the ultimate cosmic bullets, fired by supermassive black holes with enough energy to obliterate anything in their path. The process begins when a binary star system ventures too close to a supermassive black hole. The intense gravitational field tears the two stars apart in a violent cosmic dance. One star gets captured and spirals into the black hole's accretion disk, while its companion gets flung away at incredible velocity. Think of it like a cosmic slingshot effect, but with energies that dwarf anything we can imagine. The most extreme example discovered so far is a star-designated S5 HVS1, which rockets through space at over 1,700 miles per second. This stellar bullet moves so fast, it would cross the entire diameter of Earth in less than 8 seconds. The star originated from our galaxy's central black hole and has been traveling for over 33 million years, covering a distance of nearly 200,000 light years. What makes these hypervelocity stars particularly unsettling is their abundance. Scientists have identified dozens of confirmed hypervelocity stars, with hundreds more candidates awaiting verification. Each one represents a violent ejection event from a supermassive black hole, suggesting that these cosmic cannons fire regularly throughout the universe. Recent discoveries have revealed an even more disturbing possibility. Some hypervelocity stars appear to originate not from our own galactic center, but from the Large Magellanic Cloud, a nearby galaxy. This suggests that the supermassive black hole in that galaxy has been firing stellar bullets in our direction for millions of years. We may be sitting in the middle of an intergalactic shooting gallery. The danger posed by hypervelocity stars extends beyond their incredible velocities. These stellar projectiles can disrupt the gravitational balance of star systems they pass through, potentially ejecting planets from their orbits or sending comets and asteroids on collision courses. A hypervelocity star passing within a few light years of our solar system could gravitationally perturb the Oort cloud, sending a swarm of comets toward the inner solar system. The existence of hypervelocity stars also reveals the incredible precision of black hole violence. The gravitational interactions required to accelerate a star to these speeds while keeping it intact require an almost perfect balance of forces. Too little energy and the star remains bound to the galaxy. Too much energy and the star gets torn apart completely. Perhaps most disturbing is the realization that for every hypervelocity star we can observe, there may be countless more dark objects racing through space at similar velocities. Failed stars, rogue planets, and chunks of stellar debris could all be traveling at hypervelocity speeds, invisible until they interact with something else. Watch in horror as black holes slowly torture entire stars to death. Tidal disruption events represent some of the most spectacular and terrifying displays of black hole violence in the universe. These cosmic executions occur when a star ventures too close to a supermassive black hole and gets torn apart by the same tidal forces that would spaghettify a human body, but on a stellar scale that defies imagination. The process begins when a star drifts within the tidal radius of a supermassive black hole. For a star like our Sun approaching a black hole weighing 1 million solar masses, this critical distance lies at about 100 million miles from the event horizon. At this point, the gravitational difference between the star's near and far sides becomes stronger than the star's own gravity holding it together. The star does not die quickly. Instead, it undergoes a slow and agonizing destruction that can last for months or even years. The black hole's tidal forces stretch the star into an elongated shape, pulling material from both ends, while the star's core tries desperately to maintain its structural integrity. The stellar material gets drawn out into long streamers of hot gas that wrap around the black hole like cosmic spaghetti. As the disrupted stellar material spirals into the black hole, it heats up to temperatures exceeding 100 million degrees Fahrenheit. The friction between different layers of infall and gas creates an accretion disk that glows with the intensity of billions of suns. This feeding frenzy can outshine the entire galaxy for months, creating a beacon of destruction visible from billions of light years away. The most disturbing aspect of tidal disruption events is their efficiency. Roughly half of the star's material falls into the black hole, while the other half gets ejected at high velocity. The ejected material can reach speeds of thousands of miles per second, creating expanding shells of hot gas that would sterilize any planetary system within dozens of light years. Scientists have observed these stellar executions in real time using space-based telescopes. In 2019, astronomers witnessed a tidal disruption event in a galaxy 650 million light years away. The star, similar in size to our Sun, was systematically torn apart over several months, while telescopes recorded the entire process across multiple wavelengths of light. What makes these events particularly terrifying is their frequency. Astronomers estimate that tidal disruption events occur in any given galaxy about once every 10,000 to 100,000 years. With billions of galaxies in the observable universe, this means that stars are being torn apart by black holes somewhere in the cosmos every few seconds. The radiation from tidal disruption events can be detected across vast distances, suggesting that these stellar deaths create some of the brightest flares in the universe. The energy released during a single event can equal the total energy output of our Sun over its entire 10 billion year lifetime. Welcome to the most violent place in the universe, where matter dies screaming. The accretion disks surrounding a feeding black hole represents hell, made manifest in the cosmos. This swirling vortex of superheated matter creates temperatures and pressures so extreme that normal physics breaks down completely. Here, atoms are stripped of their electrons, molecules are torn apart at the subatomic level, and matter itself is tortured into forms that cannot exist anywhere else in the universe. The disk forms when matter falls toward a black hole, but possesses too much angular momentum to fall straight in. Instead, the material spirals inward, like water going down a cosmic drain, but this drain leads to oblivion. As the matter orbits closer to the black hole, it accelerates to incredible speeds, sometimes reaching 30% the speed of light. The friction between different layers of the disk creates temperatures that dwarf the cores of stars. The innermost regions of the disk reach temperatures exceeding 1 billion degrees Fahrenheit, hot enough to fuse any element in the periodic table. At these temperatures, matter exists in a plasma state where electrons are completely separated from atomic nuclei, creating a soup of charged particles that glows with the intensity of trillions of suns. The disk extends outward from just outside the event horizon to distances that can span several light years. The outer regions remain relatively cool at only a few million degrees, but even these cool areas would instantly vaporize any known material. The temperature gradient across the disk creates a hellish rainbow of electromagnetic radiation, from radio waves in the outer regions to gamma rays near the center. What makes accretion disks truly terrifying is their magnetic fields. The swirling charged particles create magnetic field lines that get twisted and tangled by the disk's rotation. These magnetic fields can become so intense that they launch jets of plasma at nearly the speed of light, creating cosmic flame throwers that can extend for millions of light years. The disk's rotation creates a phenomenon called frame dragging, where the black holes spin, literally drag space-time around with it. This effect becomes so strong near the event horizon that nothing can remain stationary relative to distant observers. Even light gets dragged along with a rotating space-time, creating a region called the ergosphere, where the normal concepts of space and time become meaningless. The violence within accretion disks exceeds anything we can imagine. Matter experiences gravitational forces millions of times stronger than Earth's gravity, accelerations that would crush any solid object into individual atoms, and radiation fields intense enough to strip electrons from atoms at the molecular level. Perhaps most disturbing is the dis's efficiency as a cosmic furnace. Nuclear fusion in stars converts less than 1% of matter into energy, but accretion disks can convert up to 40% of infalling matter into pure energy. This makes them the most efficient energy production mechanism in the universe. Near a black hole, time itself becomes a weapon of psychological torture. Time dilation represents one of the most mind-bending and terrifying aspects of black hole physics. As you approach the event horizon, time slows down relative to the outside universe in ways that would drive any conscious being to madness. This is not science fiction, but hard physics, a consequence of Einstein's general relativity that transforms time from a constant into a variable nightmare. The effect begins subtly as you approach the black hole. At a distance of 10 event horizon radii, time passes only slightly slower than normal. But as you fall closer, the time dilation becomes more pronounced. At 3 event horizon radii, time moves at about half the rate experienced by distant observers. At 2 radii, it slows to 1/3 normal speed. The horror intensifies as you approach the event horizon itself. Here, time dilation approaches infinity. From your perspective, you experience time normally. But to anyone watching from a safe distance, you appear to slow down dramatically. Your movements become sluggish, your voice drops to lower frequencies, and your image fades as the light from your body gets stretched to longer wavelengths. This creates a disturbing paradox. You never actually see yourself cross the event horizon from an outside perspective. Instead, you appear to freeze at the boundary, your image becoming progressively redder and dimmer until it fades into invisibility. Yet, from your own reference frame, you pass through the event horizon in finite time and continue falling toward the singularity. The psychological implications are staggering. Imagine trying to communicate with someone falling into a black hole. Their messages would arrive at increasingly long intervals, with each transmission more redshifted than the last. Eventually, their words would be stretched to radio wavelengths, then to infrared, until their communications fade beyond detection. Even more disturbing is what you would experience during the fall. As you approach the event horizon, you would see the universe outside the black hole speeding up dramatically. Stars would live and die in what seems like moments. Galaxies would evolve and change before your eyes. The cosmic microwave background radiation would blue shift to higher energies, eventually becoming a torrent of deadly gamma rays. The time dilation effect creates a one-way information barrier. Light signals from the outside universe can reach you, but your signals cannot reach the outside. You become trapped in a temporal prison where you can observe the universe aging around you, but cannot communicate with it. Perhaps most unsettling is the realization that time dilation affects not just your perception, but your biological processes. Your metabolism, brain function, and cellular repair mechanisms all slow down from an outside perspective. You would age more slowly relative to the outside universe, But this apparent gift comes with the ultimate price of complete isolation from the rest of reality. The time dilation near black hole reveals that time is not the constant we assume it to be, but a flexible dimension that can be stretched and compressed by gravity. Deep in the constellation, Canes Venatici lurks a monster that weighs more than our entire galaxy. Toon 6718 represents the pinnacle of cosmic horror. A hyperluminous quasar powered by a supermassive black hole, so massive it challenges our understanding of how such monsters can exist. This beast weighs over 40 billion times more than our Sun, making it one of the most massive objects ever discovered in the universe. The numbers alone are staggering. The event horizon of this monster spans nearly 800 astronomical units across, meaning you could fit the entire orbit of Neptune inside it with room to spare. If you could somehow travel at the speed of light, it would take you over 6 hours to cross from one side of the event horizon to the other. But the true horror lies in this black hole's appetite. Toon 6718 devours matter at a rate that defies comprehension, consuming the equivalent of our entire Sun every single day. This feeding frenzy creates an accretion disk so bright that it outshines 400 trillion suns combined. The energy output is so immense that we can detect it from over 10 billion light years away. The gravitational field around this monster warps space, time to an almost unimaginable degree. At the event horizon, the escape velocity equals the speed of light. But the tidal forces are so intense that they would tear apart any known material long before it reached that boundary. The gravitational gradient near this black hole is steep enough to stretch a human body across thousands of miles in mere seconds. What makes TONS 618 particularly terrifying is its age. The light we see from this quasar began its journey when the universe was less than 1 billion years old, meaning this monster formed during the cosmic dawn. How a black hole could grow to such tremendous size so quickly after the Big Bang remains one of the greatest mysteries in astrophysics. The accretion disk surrounding this black hole creates a cosmic lighthouse that can be seen from nearly the edge of the observable universe. The disk itself spans several light years, creating a swirling vortex of superheated matter that glows with temperatures exceeding 1 billion degrees. The magnetic fields generated by this disk are so intense they could launch jets of plasma at speeds approaching the speed of light. The gravitational influence of TONS 1618 extends far beyond its immediate vicinity. This monster could gravitationally bind entire star clusters and even small galaxies, forcing them to orbit around it like cosmic moths drawn to a flame. Any star system within thousands of light years would be subjected to intense tidal forces and deadly radiation. Perhaps most disturbing is the realization that TONS 618 represents just one example of ultramassive black holes that may exist throughout the universe. These cosmic titans challenge our models of black hole formation and growth, suggesting that the universe contains monsters even more terrifying than we imagine. In the heart of the Phoenix cluster sits a black hole that may weigh 100 billion suns. Phoenix A represents the current champion in the cosmic heavyweight division, a supermassive black hole so massive that it stretches the very definition of what we thought possible. Located 5.7 billion light years from Earth, this monster potentially contains more mass than some entire galaxy clusters, making it the most massive black hole ever discovered. The scale of this object transcends human comprehension. With an estimated mass of 100 billion solar masses, Phoenix A weighs more than twice as much as Tons 6018 and over 20 Zarazan times more than the black hole at the center of our own galaxy. If you could somehow replace our sun with this monster, its event horizon would extend past the orbit of Neptune. The event horizon of Phoenix A spans approximately 1/950 astronomical units, making it larger than some small star systems. Light traveling at 186 Zarazan miles per second would take over 13 hours to cross from one side of this boundary to the other. The gravitational field at this distance is so intense that time dilation effects would become noticeable to any observer. What makes Phoenix particularly horrifying is its location within the Phoenix cluster, one of the most massive galaxy clusters in the known universe. This cluster contains thousands of galaxies, all gravitationally bound together in a cosmic web of dark matter and hot gas. Phoenix A sits at the center of this cluster like a cosmic spider, its gravitational influence extending across millions of light years. The black hole appears to be actively feeding on the hot gas that fills the cluster. This intergalactic medium, heated to temperatures of tens of millions of degrees, provides a nearly inexhaustible supply of material for the monster to consume. The feeding process creates radio jets that extend millions of light years from the black hole, carving cavities in the cluster gas that can be detected by radio telescopes on Earth. The formation of such a massive black hole remains one of the greatest puzzles in modern astrophysics. Traditional models of black hole growth suggest that it should take longer than the age of the universe for a black hole to reach such tremendous size. Phoenix challenges these models and forces scientists to consider new mechanisms for rapid black hole growth in the early universe. The gravitational effects of Phoenix A extend far beyond its immediate environment. This monster helps regulate the temperature and density of gas throughout the entire Phoenix cluster, effectively controlling star formation in thousands of galaxies. Its influence shapes the evolution of an entire cluster containing more mass than 10 Zarazan Milky Way galaxies. Perhaps most disturbing is the possibility that Phoenix A represents just the tip of the iceberg. If black holes can grow to 100 billion solar masses, what prevents them from becoming even larger? The universe may contain black holes weighing trillions of solar masses, monsters so massive they dwarf entire galaxy clusters. When supermassive black holes feed, they create death rays that can sterilize entire galaxies. Quasars represent the most violent and energetic phenomena in the universe, powered by supermassive black holes that have awakened from dormancy to begin feeding frenzies of cosmic proportions. These monsters create a accretion disk so bright they can outshine their entire host galaxies, becoming beacons of destruction visible from billions of light years away. The name quasar comes from quasi-stellar radio source, because these objects initially appeared as star-like points of light in early radio surveys. However, Their true nature is far more terrifying. Quasars are actually the active cores of distant galaxies where supermassive black holes are devouring vast quantities of matter and converting it into pure energy through the most efficient process known in the universe. The energy output of a typical quasar exceeds that of 1 trillion suns. The most powerful quasars can be 10,000 times brighter than our entire Milky Way galaxy, which contains over 100 billion stars. This energy comes from matter falling into the black hole's accretion disk, where gravitational forces accelerate in falling material to speeds approaching the speed of light. The accretion disk around a quasar creates a cosmic furnace where temperatures exceed 1 billion degrees Fahrenheit. At these temperatures, matter exists in a plasma state where atomic nuclei are stripped completely bare of electrons. The resulting radiation spans the entire electromagnetic spectrum from radio waves to gamma rays, creating a torrent of deadly energy that would sterilize any planet within thousands of light years. Many quasars also produce relativistic jets, narrow beams of plasma that shoot out from the black hole's poles at speeds exceeding 99% the speed of light. These jets can extend for millions of light years, creating cosmic death rays that punch through intergalactic space like cosmic laser beams. The energy carried by these jets equals the total energy output of millions of stars. The radiation from quasars is so intense that it can completely halt star formation in their host galaxies. The energy heats and disperses the gas clouds that would normally collapse to form new stars, effectively sterilizing the galaxy. This process, called quasar feedback, can shut down star formation for millions of years, leaving behind a dead galaxy filled with aging stars. Perhaps most disturbing is the realization that quasars were much more common in the early universe. Observations reveal that the quasar population peaked when the universe was only a few billion years old, suggesting that supermassive black holes were much more active during the cosmic dawn. This early epoch represents a time when the universe was filled with these cosmic death rays. The energy from quasars can be detected across the entire electromagnetic spectrum, but their most deadly emissions come in the form of high-energy gamma rays and X-rays. These forms of radiation can penetrate deep into planetary atmospheres, destroying ozone layers and sterilizing any life forms exposed to them. The most terrifying aspect of quasars is their unpredictability. A dormant supermassive black hole can suddenly become active if it encounters a new source of matter, transforming a quiet galaxy into a cosmic death ray almost overnight. When two black holes spiral toward each other, they create the most violent events since the Big Bang. Binary black hole mergers represent the ultimate cosmic catastrophe. Events so violent, they shake the very fabric of space-time itself. These collisions release more energy and gravitational waves than all the stars in the observable universe produce in light, creating ripples in space-time that can be detected billions of light years away. The process begins when two black holes orbit each other in a deadly dance that can last for billions of years. As they spiral inward, they lose energy through gravitational wave radiation, causing their orbits to decay. The closer they get, the faster they orbit, until, in the final moments, they whip around each other at speeds approaching the speed of light. The final coalescence happens in a fraction of a second, but the energy released during this brief moment is staggering. A typical binary black hole merger converts about 3 solar masses worth of matter into pure gravitational wave energy. This energy gets radiated away as ripples in space-time that propagate outward at the speed of light. The gravitational waves from these mergers carry information about the black hole's masses, spins, and orbital dynamics. When these waves pass through Earth, they stretch and compress space itself by amounts smaller than 1/10,000th the width of a proton. Yet despite their incredible subtlety, these waves represent the most violent events in the universe. The most massive black hole merger ever detected involved 2 monsters weighing 85 and 66 solar masses respectively. The collision created a final black hole weighing about 140 solar masses, meaning that approximately 11 solar masses worth of matter was converted into gravitational wave energy in less than a second. What makes these collisions truly terrifying is their effect on the surrounding environment. The gravitational waves generated during the merger can disrupt any matter within hundreds of light years, potentially triggering supernovas in nearby stars or ejecting planets from their orbits. The space-time distortions are so severe that they can create regions where the normal laws of physics temporarily break down. The merger also creates a phenomenon called a gravitational wave kick. When 2 black holes with different spins collide, the resulting black hole can be ejected from the collision at speeds exceeding 1,000 miles per second. This creates a rogue black hole that travels through space at hypervelocity, potentially disrupting any star systems it encounters. Perhaps most disturbing is the realization that binary black hole mergers may trigger the formation of even more massive black holes. The collision can send shockwaves through nearby gas clouds, triggering gravitational collapse that forms new black holes. This process could create a cascade effect where one merger leads to multiple new black holes. The frequency of these cosmic catastrophes is higher than initially expected. Gravitational wave detectors observe binary black hole mergers at a rate of roughly 1 per week, suggesting that these violent events are occurring constantly throughout the universe. The universe itself screams in pain when black holes collide. Gravitational waves represent the universe's most primal form of communication, ripples in the fabric of space-time that carry messages of cosmic violence across billions of light years. These waves travel at the speed of light, stretching and compressing space itself as they propagate through the universe. When they reach Earth, they reveal the existence of cataclysmic events that occurred in the distant past. The detection of gravitational waves required building the most sensitive instruments ever created. The Laser Interferometer Gravitational Wave Observatory uses laser beams to measure changes in distance smaller than 1/10,000th the width of a proton. This incredible precision allows scientists to detect the space-time ripples created by colliding black holes billions of light years away. Each gravitational wave detection tells a story of cosmic destruction. The waves carry information about the masses and spins of the colliding black holes, their orbital dynamics, and the energy released during the merger. Scientists can reconstruct the entire collision from these ripples, watching as two massive objects spiral toward each other and merge in a violent explosion of gravitational energy. The first gravitational wave detection, designated GW 14912, revealed the collision of two black holes weighing 36 and 29 solar masses. The merger occurred 1.3 billion years ago when multicellular life was just beginning to emerge on Earth. The gravitational waves from this ancient collision traveled through space for over 1 billion years before reaching our planet. What makes gravitational waves particularly terrifying is their ability to carry information about events that would otherwise be invisible. Black holes normally emit no light, making them undetectable by traditional telescopes. But when they collide, they create gravitational waves that can be detected even when the merger occurs in the distant universe behind opaque clouds of gas and dust. The energy carried by gravitational waves is enormous. A typical black hole merger releases more energy and gravitational waves than all the stars in the observable universe emit in light. This energy propagates outward as ripples in space-time, carrying the signature of the collision across cosmic distances. The detection of gravitational waves has revealed that the black hole mergers occur much more frequently than previously thought. The universe experiences these cosmic catastrophes at a rate of roughly 1 per minute, meaning that space-time is constantly being disturbed by the violent death throes of massive objects. Perhaps most disturbing is the realization that gravitational waves represent just one form of cosmic messenger. The universe may be filled with other forms of space-time disturbance that we have not yet learned to detect. Dark matter interactions, colliding neutron stars, and even the expansion of the universe itself may create gravitational wave signatures that carry information about phenomena beyond our current understanding. The ability to detect gravitational waves has opened a new window into the universe's most violent events, but it has also revealed the existence of hidden cosmic forces that shape reality on the largest scales. Something massive and invisible is pulling our galaxy toward an unknown fate. Deep in the zone of avoidance, hidden behind the disk of our own galaxy, lurks a gravitational anomaly so massive it defies explanation. The Great Attractor represents one of the most disturbing mysteries in modern cosmology. A region of space that contains the mass of tens of thousands of galaxies but remains largely invisible to our telescopes. This cosmic monster sits about 250 million light years away in the direction of the constellation Hydra. Its gravitational field is so powerful that it influences the motion of galaxies across hundreds of millions of light years, including our own Milky Way. We are falling toward this invisible mass at a speed of over 400 miles per second, drawn by a gravitational force that we cannot fully understand. The Great Attractor reveals itself through the peculiar motions of galaxies in our local region of the universe. According to Hubble's law, galaxies should be moving away from us at speeds proportional to their distance. However, observations reveal that galaxies in a huge volume of space are all flowing toward the same region, as if being pulled by an enormous gravitational source. What makes the Great Attractor particularly terrifying is its hidden nature. The object lies behind the zone of avoidance, a region of sky obscured by the dust and gas in our own galaxy's disk. This cosmic curtain prevents us from seeing what lies beyond, creating a blind spot in our view of the universe where something massive and mysterious lurks. Recent observations using radio and X-ray telescopes have begun to penetrate this cosmic veil, revealing a complex structure of galaxy clusters and superclusters. The Great Attractor appears to be associated with the normal cluster, a massive collection of galaxies that may contain several supermassive black holes. However, the visible matter in this region cannot account for the enormous gravitational field required to influence such a large volume of space. The most disturbing possibility is that the Great Attractor contains a concentration of dark matter far more massive than anything previously discovered. Dark matter, which makes up about 85% of all matter in the universe, interacts only through gravity and remains invisible to all forms of electromagnetic radiation. A massive dark matter halo could create the observed gravitational effects while remaining completely undetectable. The gravitational influence of the Great Attractor extends far beyond our local galaxy group. Entire galaxy clusters containing thousands of galaxies are being drawn toward this invisible mass, creating a cosmic flow that spans hundreds of millions of light years. This motion suggests that the Great Attractor may be part of an even larger structure that shapes the distribution of matter on the largest scales. Perhaps most unsettling is the realization that our galaxy's ultimate fate may be determined by this invisible monster. As we fall toward the Great Attractor, we may eventually be drawn into a region of space where the gravitational fields become so intense that they disrupt the structure of the Milky Way itself. In the first second after the Big Bang, the universe may have created monsters that still lurk in the darkness. Primordial black holes represent the ultimate cosmic horror, because they could be hiding anywhere in the universe. Formed not from stellar collapse, but from the violent fluctuations of the early universe itself. These ancient monsters may have been created in the first fraction of a second after the Big Bang, making them older than stars, planets, and possibly even the fundamental particles that make up ordinary matter. The formation of primordial black holes required conditions of extreme density and pressure that existed only in the primordial universe. During the first second after the Big Bang, random fluctuations in the density of matter could have created regions so dense that they collapsed directly into black holes without ever forming stars. These primordial monsters could range in mass from less than an asteroid to millions of times the mass of our Sun. What makes primordial black holes particularly terrifying is their potential abundance. Theoretical models suggest that they could make up a significant fraction of the dark matter in the universe, meaning that these invisible monsters could outnumber visible stars by a vast margin. They could be lurking in the space between stars in the outer reaches of our solar system, or even passing through Earth itself. The smallest primordial black holes would have masses comparable to mountains, but would be smaller than atomic nuclei. These microscopic monsters would be virtually impossible to detect directly, but their gravitational effects could still influence the motion of larger objects. A primordial black hole passing through our solar system could potentially disrupt planetary orbits or send comets and asteroids on collision courses with Earth. Intermediate mass primordial black holes could pose an even greater threat. These monsters would weigh between 1,000 and 100,000 times the mass of our Sun, making them far more massive than any stellar black hole, but smaller than supermassive black holes. If one of these objects passed through our galaxy, it could gravitationally disrupt star formation, trigger supernovas, or even eject star systems from the galaxy entirely. The largest primordial black holes could have provided the seeds for the supermassive black holes we observe at the centers of galaxies today. These monsters would have had a significant head start in the cosmic race to grow large, potentially explaining how supermassive black holes could form so quickly in the early universe. Perhaps most disturbing is the realization that primordial black holes could be completely undetectable until they interact with other matter. Unlike stellar black holes, which often reveal themselves through X-ray emission from accretion disks, primordial black holes formed in the empty space between galaxies would remain invisible until they encountered a source of matter to consume. The search for primordial black holes has become one of the most important quests in modern astrophysics. These ancient monsters could hold the key to understanding dark matter, the formation of the first galaxies, and the ultimate fate of the universe itself. The universe hides a terrifying population of missing, linked black holes that we are only beginning to discover. Between the stellar mass black holes formed from dying stars and the supermassive monsters at galactic centers lies a mysterious gap that represents one of the most unsettling puzzles in modern astrophysics. Intermediate mass black holes, weighing between 100 and 100,000 times the mass of our Sun, should exist in large numbers throughout the universe, but they remain stubbornly difficult to find. This missing population represents a cosmic horror story because these intermediate mass black holes could be hiding in plain sight. Unlike their smaller stellar cousins, which often reveal themselves through X-ray emissions from companion stars, or their supermassive relatives which power bright quasars and active galactic nuclei, intermediate mass black holes could remain invisible while lurking in the darkest corners of the universe. The few intermediate mass black holes that have been discovered reveal the terrifying potential of these cosmic predators. One candidate, 3-224, weighs about 50,000 times the mass of our Sun and sits in the outskirts of a distant galaxy. This monster appears to be slowly consuming a nearby star, creating periodic flares of X-ray radiation that betray its presence. What makes intermediate mass black holes particularly dangerous is their potential mobility. Unlike supermassive black holes, which sit anchored at the centers of galaxies, intermediate mass black holes could be wandering through space as rogue objects. These cosmic nomads could have been ejected from their original locations by gravitational interactions with other black holes, or by the asymmetric emission of gravitational waves during mergers. The formation mechanisms for intermediate mass black holes remain mysterious and disturbing. They could form through the direct collapse of the first generation of stars in the early universe, through the merger of multiple stellar mass black holes, or through the accretion of matter onto primordial black holes. Each formation scenario suggests a different population of these monsters lurking in the cosmic darkness. Perhaps most terrifying is the possibility that intermediate mass black holes could be hiding in globular clusters, dense collections of stars that orbit around galaxies. These ancient star clusters contain hundreds of thousands of stars packed into regions only a few dozen light years across. The gravitational dynamics within these clusters could have led to the formation of intermediate mass black holes through stellar collisions and mergers. The discovery of intermediate mass black holes would fill in the missing link between stellar and supermassive black holes. But it would also reveal that the universe contains a vast population of invisible predators that we have barely begun to detect. These monsters could outnumber both stellar and supermassive black holes, creating a hidden ecosystem of cosmic destruction. The search for intermediate mass black holes has intensified with the detection of gravitational waves, which provide a new way to observe black hole mergers across the universe. Future gravitational wave detectors may reveal the existence of these missing link monsters in large numbers, wandering through the cosmic darkness, or black holes that have been ejected from their galaxies like bullets from a gun. Rogue black holes represent the ultimate cosmic nightmare because they combine the destructive power of black holes with the unpredictability of objects moving at hypervelocity through space. These monsters have been ejected from their original galaxies by violent gravitational interactions, creating cosmic wanderers that travel through the universe at speeds exceeding 1,000 miles per second. The ejection process begins when supermassive black holes undergo close encounters with other massive objects. When two galaxies merge, their central black holes can engage in a complex gravitational dance that sometimes results in one or both black holes being flung out of the newly formed galaxy. The gravitational slingshot effect can accelerate these monsters to speeds high enough to escape their host galaxy entirely. The most terrifying aspect of rogue black holes is their invisibility. Without the hot accretion disks that make feeding black holes visible, these cosmic wanderers drift through intergalactic space as completely dark objects. They can only be detected if they pass in front of background stars, creating brief gravitational lensing events that bend and magnify the starlight. Scientists estimate that there could be billions of rogue black holes wandering through the universe, ejected from their galaxies during the violent merger processes that have shaped cosmic structure over billions of years. These monsters carry the gravitational memory of their violent past, traveling through space like cosmic cannonballs fired by galactic collisions. The danger posed by rogue black holes extends far beyond their immediate destructive power. A rogue black hole passing through our galaxy could gravitationally disrupt the orbits of stars, potentially ejecting some star systems from the galaxy entirely. If a rogue black hole passed through the outer regions of our solar system, it could disturb the Oort cloud, sending a swarm of comets toward the inner solar system. The discovery of rogue black holes has been aided by gravitational wave detectors, which can observe the mergers of black holes throughout the universe. Some of these detected mergers may involve rogue black holes that have been wandering through space for billions of years before encountering other massive objects. Perhaps most disturbing is the realization that rogue black holes could be much more common than we initially thought. The violent processes that create these cosmic wanderers may have been operating since the early universe, when galaxy formation and mergers were much more frequent. This suggests that intergalactic space may be populated with vast numbers of invisible predators. The speed of rogue black holes makes them particularly dangerous. Moving at thousands of miles per second, these monsters could cross the entire solar system in a matter of months. Their approach would be virtually undetectable until they began to gravitationally influence nearby objects, leaving little time for any form of response or preparation. The existence of rogue black holes transforms our understanding of cosmic safety. Space is not empty, but filled with invisible monsters that could emerge from any direction at any time. Some black holes create million light-year death beams that can sterilize entire regions of the universe. Relativistic jets represent the most destructive weapons in the cosmic arsenal. Streams of plasma accelerated to 99% the speed of light by the incredible magnetic fields generated around spinning black holes. These cosmic flamethrowers can extend for millions of light years, carrying enough energy to power entire galaxies and creating zones of destruction that persist for millions of years. The formation of these jets begins with the rotation of the black hole itself. As the monster spins, it drags the surrounding space-time around with it, creating a phenomenon called frame dragging. This rotation, combined with the magnetic fields generated by the accretion disk, creates a cosmic dynamo that accelerates charged particles to relativistic speeds. The jets emerge from the black hole's poles in two narrow beams that maintain their coherence across incredible distances. The particles within these jets move so fast that they experience extreme relativistic effects, including time dilation and length contraction. From the perspective of the particles, the journey across millions of light years happens in a much shorter time due to these relativistic effects. The energy carried by these jets is staggering. A typical galactic jet carries more energy than the total output of billions of stars, concentrated into a beam only a few thousand light years wide. This energy density is so high that it can heat intergalactic gas to temperatures exceeding 100 million degrees, creating cavities in the cosmic web that can be detected by X-ray telescopes. What makes these jets particularly terrifying is their ability to affect entire galaxy clusters. When a jet encounters the hot gas that fills the space between galaxies, it creates shock waves that propagate outward at thousands of miles per second. These shock waves can trigger star formation in some regions while completely shutting it down in others, effectively controlling the evolution of galaxies across millions of light years. The jets also create radio lobes, massive regions of space filled with high-energy particles that emit radio waves. These lobes can be larger than entire galaxies and persist for millions of years after the jet activity has stopped. Any planet or star system within these radio lobes would be bombarded with deadly radiation that could sterilize all life forms. Perhaps most disturbing is the directionality of these cosmic weapons. While the jets are narrow and focused, they can change direction as the black holes spin access precesses over time. This means that regions of space that were previously safe from the jet's deadly radiation could suddenly find themselves in the line of fire. The discovery of jets extending over 100 million light years from their source black holes reveals the incredible reach of these cosmic weapons. These ultra-long jets can affect the structure of the universe on the largest scales, carving channels through the cosmic web and redistributing matter and energy across vast distances. The existence of galactic jets transforms our understanding of black holes from simple gravitational monsters into cosmic engines capable of reshaping the universe itself. Deep in the Phoenix cluster, a black hole demonstrates how radio jets could sterilize entire galaxies. The Phoenix cluster represents a cosmic laboratory for understanding how supermassive black holes can control the fate of entire galaxy clusters through their radio jets. This massive collection of galaxies, located 5.7 billion light years from Earth, contains some of the most extreme examples of black hole feedback ever observed, revealing the terrifying potential for these monsters to regulate star formation across millions of light years. At the center of the Phoenix cluster sits the supermassive black hole Phoenix A, which creates radio jets that extend for millions of light years in both directions. These jets carve massive cavities in the hot gas that fills the space between galaxies, creating bubbles of low-density plasma that can be detected by radio telescopes on Earth. The energy required to create these cosmic bubbles is staggering. The Phoenix cluster's central black hole must pump about 10 to the 45 joules of energy into its surroundings every second, equivalent to the energy output of 10 billion suns. This energy gets deposited into the intergalactic medium, heating it to temperatures exceeding 100 million degrees Fahrenheit. The radio jets from Phoenix A create a feedback mechanism that regulates star formation throughout the entire cluster. The energy from the jets heats the gas between galaxies, preventing it from cooling and condensing into new stars. This process can completely shut down star formation in galaxies across the entire cluster, leaving them filled with aging stars that gradually fade without being replaced. What makes the Phoenix cluster particularly terrifying is its demonstration of how black hole feedback can operate on cluster scales. The radio jets from the central black hole affect not just the immediate galaxy, but thousands of other galaxies distributed across millions of light years. This represents cosmic scale environmental control by a single supermassive black hole. The jets also create pressure waves that propagate through the cluster gas at speeds of thousands of miles per second. These shock waves can trigger star formation in some regions while completely suppressing it in others, effectively sculpting the distribution of stellar populations across the entire cluster. The Phoenix cluster reveals what could happen if our own galactic center became more active. If Sagittarius A star began producing jets similar to those seen in Phoenix A, the energy output could heat the gas throughout the Milky Way, potentially shutting down star formation in our entire galaxy. The radiation from such jets could also pose a direct threat to any planets within thousands of light years. Perhaps most disturbing is the realization that the Phoenix cluster may represent the future of all galaxy clusters. As supermassive black holes continue to grow and merge, they may eventually reach masses large enough to completely regulate the gas content of their host clusters. This could lead to a universe filled with dead galaxy clusters where star formation has been permanently shut down. The Phoenix cluster demonstrates that black holes are not just local threats, but cosmic forces capable of controlling the evolution of structure on the largest scales in the universe. In the far future, black holes will grow so massive, they will devour entire galaxy clusters. The ultimate fate of black holes in our universe represents a cosmic horror story that unfolds over trillions of years. As the universe continues to expand and cool, stars will eventually stop forming, galaxies will merge, and the supermassive black holes at their centers will continue to grow until they become monsters of unimaginable size and power. Current models predict that supermassive black holes will continue to gain mass through several mechanisms. Galaxy mergers will cause their central black holes to merge, creating even more massive monsters. The gradual accretion of gas, dust, and even entire stars will add to their mass over cosmic time. Most significantly, the expansion of the universe will eventually bring more and more matter within reach of these gravitational titans. In the far future, when the universe is 10 times its current age, the largest black holes may weigh over 100 trillion times the mass of our Sun. These stupendously large black holes will have event horizons spanning light years, making them larger than many current star systems. The gravitational influence of these monsters will extend across hundreds of thousands of light years, effectively controlling the dynamics of entire galaxy clusters. The growth of these future black holes will fundamentally alter the structure of the universe. As they consume more matter, their gravitational influence will extend farther and farther, eventually reaching the point where they can capture and devour entire galaxies. The process will be slow but inexorable, with galaxies spiraling into these cosmic monsters over timescales of hundreds of billions of years. The feeding process will create accretion disks larger than current galaxy clusters, with temperatures and luminosities that dwarf anything we observe today. These future feeding frenzies will produce jets of relativistic plasma that extend for billions of light years, creating cosmic death rays that can sterilize entire regions of the universe. Perhaps most terrifying is the realization that these future black holes will eventually merge with each other, creating gravitational wave signals so powerful they could potentially tear apart the fabric of space-time itself. The collision of two stupendously large black holes would release more energy than the Big Bang, creating ripples in space-time that could fundamentally alter the properties of the universe. The ultimate endpoint of this growth process is the formation of a single universe-spanning black hole that contains all the matter and energy in the cosmos. This final black hole would have an event horizon larger than the current observable universe, representing the ultimate victory of gravity over all other forces. The time scales involved in this cosmic evolution are almost beyond comprehension. The process will take longer than the current age of the universe by factors of millions or billions. Yet the inevitability of this outcome makes it no less terrifying. The growth of future black holes represents the ultimate cosmic destiny. The future where the universe itself becomes a single, all-consuming monster that devours everything that has ever existed. The universe may already contain black holes so massive they challenge our understanding of physics itself. Stupendously large black holes represent the theoretical upper limit of cosmic horror. Monsters so massive they strain the very foundations of our understanding of gravity, space-time, and the structure of the universe. These hypothetical titans would weigh over 100 billion solar masses, making them larger than entire galaxy clusters and approaching the mass of the observable universe itself. The existence of such monsters would require formation mechanisms that go beyond anything we currently understand. Traditional black hole growth through stellar evolution and galactic mergers cannot account for objects of this size within the current age of the universe. These stupendously large black holes would need to form through direct collapse of entire regions of the early universe, or through exotic processes involving dark matter and dark energy. The event horizon of a stupendously large black hole weighing 1 trillion solar masses would span over 100 light years, making it larger than the distance between our sun and the nearest star. The gravitational field of such a monster would be so intense that it could bind entire galaxy clusters, forcing thousands of galaxies to orbit around it like cosmic particles in a gigantic atom. The tidal forces around these monsters would operate on galactic scales. Individual galaxies approaching a stupendously large black hole would be stretched and distorted by tidal forces, creating streams of stars and gas that spiral into the monster's accretion disk. The process would be visible as a gradual dismantling of galactic structure across millions of light years. The accretion disk around a stupendously large black hole would be a cosmic structure unlike anything in the current universe, spanning hundreds of thousands of light years and containing the mass of millions of galaxies. This disk would glow with the intensity of quadrillions of suns. The magnetic fields generated by such a disk would be strong enough to accelerate particles to energies that approach the theoretical limits of physics. Perhaps most disturbing is the possibility that stupendously large black holes could already exist in the current universe, hidden in regions of space where their effects have not yet been detected. These monsters could be lurking in the cosmic web, masquerading as dark matter concentrations or hiding behind the cosmic microwave background radiation. The discovery of stupendously large black holes would revolutionize our understanding of cosmology and fundamental physics. Objects of this size would probe the limits of general relativity, potentially revealing new physics that governs the behavior of matter and energy at the largest scales. The gravitational waves produced by merging stupendously large black holes would carry energies that could affect the expansion of the universe itself. These cosmic collisions might be responsible for some of the mysterious aspects of dark energy and the accelerating expansion of space. The existence of stupendously large black holes would also raise profound questions about the ultimate fate of the universe. If such monsters already exist, they may represent the future state of all matter and energy in the cosmos. These theoretical titans represent the absolute pinnacle of cosmic terror. Objects so massive and powerful that they transcend our current understanding of reality itself. Black holes will outlive stars, galaxies, and possibly the universe itself in a cosmic game of ultimate survival. The connection between black holes and the heat death of the universe represents the ultimate cosmic horror story, a tale of eternal predators that will persist long after every star has burned out and every galaxy has faded into darkness. While the universe marches toward maximum entropy and thermal equilibrium, black holes will continue to grow, merge, and dominate the cosmos for time scales that make the current age of the universe seem like a brief moment. In the far future, when the universe is 10 to the 14 years old, star formation will have completely ceased. The last red dwarf stars will have exhausted their nuclear fuel and faded to cold white dwarf remnants. Galaxies will have merged into massive elliptical systems, and the only remaining sources of energy will be the occasional collision of dead stars and the slow feeding of supermassive black holes. During this dark age, black holes will become the dominant form of matter in the universe. They will continue to grow through the accretion of cold gas, dust, and stellar remnants, gradually consuming everything in their vicinity. The merger of black holes will create gravitational wave signals that represent the only remaining form of energetic activity in the dying universe. The black holes themselves will begin to evaporate through Hawking radiation, a quantum mechanical process that causes them to slowly leak energy back into the universe. However, this evaporation process is incredibly slow for large black holes. A black hole with the mass of our sun would take 10 to the 67 years to evaporate completely, while supermassive black holes would persist for 10 to the 100 years or more. This means that black holes will outlive the universe as we know it by factors of trillions upon trillions. They will exist in a cosmos where protons have decayed, where the cosmic microwave background has cooled to absolute zero, and where the expansion of space has separated all matter by distances measured in light years. The evaporation of black holes through Hawking radiation will provide the universe's final source of energy. As these monsters slowly shrink, they will emit particles and radiation that briefly illuminate the cosmic darkness. The smaller a black hole becomes, the faster it evaporates, leading to a final explosive burst of energy when it disappears completely. Perhaps most disturbing is the possibility that black holes represent the universe's attempt to concentrate all matter and energy into the smallest possible space, effectively reversing the expansion that began with the Big Bang. In this scenario, black holes are not just cosmic accidents, but fundamental features of a universe that is trying to return to its primordial state. The ultimate fate of black holes may determine whether the universe ends in heat death with maximum entropy and no available energy, or in a big crunch where gravity eventually overcomes expansion and everything collapses back into a single space. The connection between black holes and cosmic destiny reveals these monsters as more than just local threats, but as agents of the universe's ultimate transformation. In the universe's final moments, the last black holes will explode in bursts of Hawking radiation, marking the end of everything. The final evaporation of black holes represents the ultimate cosmic epilogue. The last chapter in the story of the universe, where even these most persistent monsters must finally surrender to the inexorable march of entropy. Through Hawking radiation, black holes slowly leak their mass energy back into the cosmos, shrinking grain by grain until they vanish in explosive bursts that illuminate the dying universe one last time. The process begins with quantum fluctuations at the event horizon, where particle-antiparticle pairs spontaneously appear from the vacuum. Normally, these pairs would annihilate each other instantly, but near a black hole, one particle can fall into the event horizon while the other escapes. This escaped particle carries away a tiny amount of the black hole's mass energy, causing it to shrink imperceptibly. For stellar mass black holes, this evaporation process is almost unimaginably slow. A black hole weighing 10 times the mass of our sun would take 10 to the 60, 7 years to evaporate completely. During most of this time, the black hole would emit radiation at a temperature barely above absolute zero, making it virtually undetectable against the cosmic background. But as a black hole shrinks, its temperature increases dramatically. The final stages of evaporation happen with startling speed. In the last second of its existence, a black hole would emit more energy than the sun produces in its entire 10 billion year lifetime. This final burst would create a flash of gamma rays, particles, and exotic radiation that would briefly outshine entire galaxies. The universe's final black holes will be the smallest ones, remnants of the primordial monsters that formed in the early universe. These microscopic black holes, no larger than atomic nuclei, but containing the mass of mountains, will be the last objects to evaporate. Their final explosions will mark the ultimate end of organized matter in the universe. After the last black hole evaporates, the universe will enter its final state, a cold, dark, and empty space filled only with elementary particles and photons. The temperature will approach absolute zero, and the density of matter will be so low that particles will rarely encounter each other. This is the heat death of the universe, the final victory of entropy over order, Perhaps most disturbing is the realization that the evaporation of black holes may not represent a true ending, but a transformation. The information that fell into black holes over cosmic time may be released during their final explosions, potentially carrying the encoded history of everything that ever existed. The universe's final act may be the revelation of all its secrets in a cascade of Hawking radiation. The terror of black holes ultimately lies not in their ability to destroy, but in their role as custodians of cosmic memory. They preserve the information of everything they consume, carrying the history of stars, planets, and potentially entire civilizations within their event horizons. When the last black hole evaporates, it will release this cosmic library back into the universe, creating a final monument to everything that ever was before the darkness claims all.